Hey, good afternoon. Letting my bologna sandwich lunch settle in. Thought I'd share a little backstory about senior chemical engineer position. What that might mean. What you might have to understand to be able to walk into a position like that. So, packed up the family, moved to Maryland, right? Beverly Hillbillies style. From Texas, no less. And walk in the door and start the first day of classes on a new generation of clustered process control system. Just the next generation in an already well-oiled machine out there within the industry. So you're working under a distributed system, distributed control system, real-time systems, a network architecture that was using a new implementation of internet, which is marginally unusual in industry at that time. It's common now. So this was the first signs of clustered computing and shared intelligence and deciding who gets what piece, because in failure mode analysis of redundant systems, you have to be able to recover from it. So you do evaluations like a failure of a disk storage array and its recovery time. If you don't have enough drives in there, it simply will not do what the salesman said or what the executive decision made. So you're going through technical evaluations of hardware up and down the spectrum of a clustered environment. You're learning about, you knew the operating systems already. You knew the network systems. You knew the basic fundamental Fortran and machine code, macro 11 libraries, huge machine libraries because of shared memory architectures among the individual controllers and the shared controllers and the backup controllers. So memory management and the amount of information you can cross pass each bus. So besides Ethernet and the commons, there was always hardwired buses, 32, 64-bit hardwired buses across for memory synchronization, because that's how critical it is. So you're walking in, you're taking all of this for granted, and you're learning. You've got some weeks ahead of you of this new system to learn about, and a set of maybe 5 new programming languages among them. New to you. They're an evolution of these program languages. So then you turn around and your first meeting, staff meeting, again, senior position. You're in charge of an area and responsible for the systems around and in that area. My peer was the site. Now this is computer systems, so we're talking computers. And right now they're in 2 buildings. There's the protagonist and the antagonist role here in these computers in doing testing for real-time systems. So my requirement was low-level interlocks. My specialty was low-level interlocks and trying to do the analysis for it. But my area was called a frit kit bin conveyor system, which fed a set of materials, ceramics, into the furnace, and elsewhere into the furnace was injected low-level nuclear waste. So the chemistry of that mix to make glass, we'll call it glass, that's what it is, it's a ceramic at that point, was fascinating, specific, and very pointed. Very, very pointed. But what I got out of it was my conveyor systems, mechanical conveyor systems, inside a part of a canyon of concrete and other process systems and equipment, black boxes, black box designs. You can look those up and find out what they are. So this low-level interlock idea is if these subsystems, the many subsystems built in other canyons that support this canyon's systems, are going to fail, what do we do? How do we handle that failure? So you're designing low-level interlocks and the scenarios that are going to go with those interlocks. You have to know these interlocks. Are they Ethernet? Are they hardwired interlocks? Are those 3 vendors supplying massive air compressors? 3 different vendors supplying the same inputs and outputs and drives. Have I got the same security and understanding the signal flow and the signal, is it good? Is it signal to noise ratios? Is it an analog or is it purely digital? Did they touch a push screen button in order to do this, affect this action? Or was it sensor? So this is introduction to. This is the realm, the breadth of what you're considering in looking at this, simply making sure a conveyor runs. Only it's a redundant conveyor. If something goes wrong, if this interlock gets tripped, it's that serious. It means that all the black boxes are done because it's right at the operating reactor. The effects of that downstream have effects. And once that reactor is done, it's done. It's so contaminated you can't go near it. The intent is to probably leave it in place for the rest of its life, which is near some 30 tons of the Earth's plutonium supply, a major amount. So this is the insight you get into. And so looking along with that project, doing all the things that senior chemical engineers do in a nuclear engineering world with due diligence. That's one of the keys there, due diligence. It's that nefarious right and wrong question, true and false. Did you do enough diligence to make sure that this piece of equipment, this major capital investment, is going to run for its design life? So you've read the design intent documents in order to be able to understand the commitments that being made within the process constraints. If you don't document those process constraints, then, well, shit happens. It's another bad day, another tidal wave you didn't expect. While Congress defunded that program and project and I left it, it didn't stop. There's a bit of insight into days in the life of 1980s